Let's consider a 1D heat conduction for a steel plate. The cross-section area is 1 square meter and with a thickness of 1 centimeter. Then it has a one-side surface maintained at the temperature, say surface 1 of 100 degrees, and another side as this, the surface 2 at 0 degree. Then we need to calculate in what the total heat transfer rate by conduction, and assume the temperature gradient along the inside the plate is linear. The plate is made by steel, and as I just mentioned, the thermal conductivity of steel is 60 watt per square meter Kelvin. For conduction problem, which equation should we use?
Q double prime conduction.
That's for Fourier's law. And as I already mentioned here, 1D conduction. So that's Fourier's law in 1D case. And in which direction is the heat flow? Does the heat flow? Because it is a plate. Assume a plate, we can see some students may get confused. It's obviously a 2D case for a plate. Why we can assume 1D heat transfer situation for this plate? In reality, the heat transfers situation is not 1D in edges. We can imagine the heat can go in 3 directions. There is not a obvious reason we can't assume it is 1D. The 1D, let's assume the point is the middle of the plate or somewhere very far from the edges. It is reasonable to assume 1D heat flow case just along the direction. But for edges, they are not. They are super complex. We need to apply the 3-dimensional heat Fourier law and do the volume integral to calculate the heat exchange rate in corners. But the error associated if we neglect those edges, the error is at the order of the thickness, which means for the cross-section area of 1 square meter, if we assume everything is purely 1D, the associated error due to edge effect is more or less like 1 centimeter thickness. It means for this surface area, cross-section area of 1 square meter, which is 10,000 square centimeters, there is more or less around 400 centimeters near the edges. The results are not accurate because they are not exactly 1D heat flow. But compared to the total surface area, it is reasonable. We can apply the 1D heat transfer, heat flow equation to make our calculation much easier and to obtain a result nearly the exact the value, but in a much simpler way. Those equations look quite simple, but they actually, if we can understand the underlying mechanisms and apply with reasonable assumptions, they can help us get very good calculation result without expensive software or your entire PhD to make a super complex simulative model to just get the 400 centimeter square area. That's the edge effect, and it is reasonable for us to neglect the edge effect and assume everything is 1D. In this case, plug in numbers. The heat exchange rate is given by the cross-section area. You asked me the question, what's the difference of cross-section area and the surface area? Can you see the difference now? The plane perpendicular to the heat flow direction. This is the cross-section area, but the total surface area, we should also consider something, the side surface and the double. So the cross-section is not equal to surface area, but when we apply Fourier's law, it's always times the surface area perpendicular to heat flow. That's the cross-section area. We cannot use surface area here. And in our exams, always write down the governing formulas first and go step by step. At the very end step, you plug in all the numbers. What's the temperature gradient? If we assume it is linear, so it's simply by the temperature difference over the characteristic length where the heat flows, which is 1 centimeter. And 100. Then the final result should be 6 watts. Yeah, sorry, it is 1 square meter. Do a small unit conversion here to convert the centimeter into meter. I got confused around here. Sorry, the result should be 6 times 10 up 5th watt.